Hi guys, thank you for attending my presentation. My name is Cheng. I'm the machine learning engineer and founder at Audoir. And in this presentation, I'm going to talk about generative AI for songwriting and music production. But first, I'd like to present you with a challenge. Can you name a popular song that you heard on the radio or from a streaming platform that has been created using AI technology? Now, if you're having a hard time naming a song, that's because the music industry hasn't really adopted this technology yet. So this leads to the question, can generative AI technology provide value for music creators? I'm going to show you that yes, it can, and there are certain things that the AI music creation tool developers need to do in order for this to happen. So here is the presentation outline. First, I'm going to give an overview of generative AI technology. Then I'm going to talk about how to build an AI that creates music. And then I'm going to go over some popular AI music creation tools that are available to be used for free. And then I'm going to talk about the challenges with the viability of AI music technology, particularly when using it in the music industry to create real music. And finally, I'm going to talk about the strategies for the adoption of AI in the music industry. Okay, so now I'll go over a brief overview of generative AI technology. Today's most advanced AI technology is deep learning. And what deep learning is, it's an artificial neural network that maps data from X into Y. So you can think of deep learning as a chain of geometric transformations or a chain of math formulas that does this X to Y mapping. This mapping is a process of automatic feature extraction. So during training, what the deep learning neural network would do is it would learn what are the relevant features of X that can be mapped into Y. So as I mentioned, training is one of the two phases of building a deep learning neural network. The other phase is the prediction or inference phase, where we feed new data X into our deep learning neural network that's been trained with data. And the deep learning neural network would then be able to predict or infer new data Y. So here's an example of generative AI in action. This is OpenAI's GPT-2. Here we can see that there is a synopsis written by a human. So you can think of this as data X. And the machine is able to take this synopsis and generate a lengthy and very realistic essay. So this is data Y. So as you can see, once the AI is trained, it's able to generate a large quantity of derivative work. So we can generate as many essays as we want using the same synopsis or a different synopsis. Basically, the generative AI technology is very powerful once it's trained to generate a large quantity of derivative work. So now we're going to take a closer look at the deep learning autoregressive deep learning model, which is an autoregressive or time series AI model. And this is used for solving time series problems. So in the case of music, what we want to try to solve is given a sequence of notes, we want to predict what is the next note. So the way that this works is that during training, each value updates an internal state as the time progresses. So the deep learning AI actually keeps an internal state, and when it sees this note, it will update the state to, let's say, gray. And in the next time step, for this note, it would update the state to orange, and so on. So during training, what's actually getting updated are these orange arrows. So the AI learns, given a sequence of notes, how to represent it internally, how to represent the state internally. And during prediction, each output is generated sequentially, and the outputs are generated based on a probability distribution. So let me show you what I mean. So here's an example of a sequence of notes, and given its training, it's able to represent that as a certain internal state. The internal state is then converted into a probability distribution, which you can think of as a set of weighted dice. You can then roll the dice to generate the next note in our sequence. Now the next note, the generated output, is usually fed back to the input to update the state. So we can feed this note back to our deep learning AI to generate another internal state, and then use this to generate the next probability distribution and the next node in the sequence. So there are some popular autoregressive AI architectures out there. There's the recurrent neural network, which has been around the longest. There's the RNN with the attention mechanism, which works slightly better. And there's the transformer, which is based purely on attention. I'm not going to go over this in detail in this presentation, but there are plenty of resources on the internet if you want more details on that. Okay, so now that we have a general knowledge of how generative AI works, let's talk about how to build an AI that creates music. And this is usually done with an autoencoder architecture. So in this architecture, we actually have two deep learning AIs. We have the encoder deep learning AI and the decoder deep learning AI. So data X is transformed into data Z using the encoder, and data Z is mapped into data Y using the decoder. And what Z is a representation of the relevant features of X that maps to Y. So let me show you what that means. So here's the same picture, but it's rotated 90 degrees. So in this picture, we have a close-up of Z. So Z is in reality a hyperdimensional vector, which means it's a math vector with many dimensions. But in this case, we're just simplifying it to 2 dimensions so you guys can see what's going on. And during training, what the autoencoder would actually do is it would map music of similar features to similar locations on this Z plane. So for example, it would map music by the Beatles to these green dots and music by Mariah Carey to these blue dots. Now, one popular technique when it comes to training the autoencoder is called reconstruction. And what we're doing here is we're mapping X to Z and back to X. So the input and output mapping is exactly the same data set. And what this allows us to do in prediction is we can remove the first half of the architecture and just use the Z to X mapping. And this allows us to generate new random music. So for example, if we can find a random point in this Z plane, then we can generate new random music. It also allows us to generate interpolated music. So what this means is that if we can find a point that's halfway between the Beatles and halfway between the Beatles and Mariah Carey, then this allows us to generate music that's about 50% Beatles and 50% Mariah Carey. Another popular technique is called transformation, where we're transforming X to Z and then to Y. And during prediction and training, it's exactly the same. So this is very similar to one of the previous slides that I shared of the X to Y mapping, except we have this intermediate state Z. So with this architecture, we have more control over how the relevant features of X are represented internally in this deep learning AI architecture. And this allows us to create from context. For example, we can map X as text to music, which is Y, or we can map a chord progression to music, or we can map a melodic motif to a full musical score. Now, as I mentioned before, deep learning AI is great at generating a large quantity of derivative work, but a lot of what's been generated is actually not usable. For example, some parts of what's generated may contain a similar sequence to, or the exact same sequence as the training data set. And so in essence, what the AI is doing is plagiarizing the training data set. And this is very bad, especially if you're using copyrighted material to train your AI, because the last thing you want is your AI to generate copyrighted material, and that makes the AI unusable. So we need some kind of plagiarism detector at the output. The other thing that we need is we need some kind of a critic, which can be built using a deep learning AI. And what the critic does is it ranks the large quantity of generated output based on quality. So this allows the user to only look at the best output out of like hundreds of output. The user maybe can only look at the top 10. So that's what's represented in this picture here. We have the AI generating a large quantity of output, and it gets filtered into this nice high quality generated output data. So now I'm going to talk about how do we represent music as data. And it turns out there's a form of representing music that's very efficient, and it's been in use since the 1930s. It's called the lead sheet, and according to Berkeley College, it's the most efficient form for communicating musical ideas. So the lead sheet doesn't contain every note of every instrument in a song. It only contains the main melody, as seen here, and the chord notation for the harmony. So it turns out you can distill the information of a song into an essential information of lead sheet. And the reason why we want to distill this information is because it makes it a lot easier for the AI to understand how to do this X to Y mapping during the training. It makes it easier for the AI to understand how to map or how to find the relevant features to do this X to Y mapping. So now that we know how to build an AI that creates music, let's take a look at some of the popular AI music creation tools that are available for you to try for free. There's Google Magenta, and Google Magenta has a suite of tools. So it has Generate, which generates melodic motifs. It has Continue, which extends melodic motifs. It has Interpolate, which merges two different melodies. Drumify adds a drum rhythm to an existing piece of music. And Groove adds a groove to an existing piece of music. There's Amazon Deep Composer, and they have a tool called Music Studio, and Music Studio does two things. One, it takes a melodic motif like Twinkle Twinkle Little Star, and is able to generate a full musical score based on a certain style, like Bach, for example. It's also able to add instrumentation to music. For example, here in this rock setting, it's able to add rock instrumentation like guitar, bass, and drums. OpenAI's MuseNet is similar to Amazon's Deep Composer. It takes a melodic motif and is able to extend it based on a certain style. So in this example, it extends it based on Chopin. And is also able to add instrumentation to the music, to the generated music. So it's able to add strings, winds, drums, etc. So Audoir SAM is different from the previous tools in that it's focused on songwriting. So the AI is trained with hit songs, and its purpose is to help artists write hit songs. So the suite of tools allows artists to the suite of tools can create music from scratch, or can create music from lyrics or text, create music from a chord progression, create music from a melodic motif. It can extend a motif, and it can transform text to lyrics. So now that we have an understanding of the technology that powers these AI music creation tools, and we've taken a look at some of the popular AI music creation tools that are available to be used for free, Let's talk about the challenges of the viability of using AI music technology, particularly when we're trying to use the technology in the music industry to create real songs for the general public. First, I'm going to talk about the inequality in the music industry. So I got this graph from Rolling Stone magazine, which shows that 90% of the streams goes to the top 1% of music artists. So what this means is that if you're a music artist and you aren't able to consistently create hit songs and be in this 1%, well, the graph over here is very flat, which means that barely anybody's going to listen to your music. So based on the music industry trends, we can observe that when we're trying to create music creation tools, the problem really is not how do we create music, but rather it's how do we create hit songs, or how do we create tools that enable artists to write hit songs. Now there are some limitations with deep learning. I got this from the Keras blog, and the example that they use is that in certain cases, the X to Y mapping is too complex for today's deep learning AI technology. For example, it's too complex for deep learning AI to map software features into software code. And this is a quote from a blog that states, anything that requires reasoning, long-term planning, algorithmic like data manipulation is out of reach for deep learning models, no matter how much data you throw at them. So we can observe a similar limitation when it comes to AI music technology. For example, it's not possible to map song topic into a hit song or pretty much anything else into a hit song. And actually, the reason why I know this is because I've actually tried this myself. And it's actually well understood in the AI music community that AI by itself is not capable of creating hit songs. So here's a quote from Verge magazine, which states that on a micro scale, the music is convincing, but the longer you listen, the less sense it makes. None of them are good enough to craft a Grammy Award-winning song on their own yet. And here's a quote from Time magazine, which states that, but while the technology has come a long way, many say that we're still far from an AI creating hit songs on its own. So one of the problems with deep learning AI is that songwriting is a sequential process. So what I mean by that is, for example, if we're trying to write a song, we will first write a motif, and then we will write additional motifs that are compatible with the first motif. Then we would form these motifs into song sections like verse, chorus, or bridge. And then finally, we would arrange these song sections into a song. So this sequential process is actually very difficult for deep learning AI to learn. And secondly, for each task, there's actually 3 different subtasks. So for example, if we're trying to write a motif, what we would do is we would actually write 10 different motifs. So that's coming up with the ideas. And then we would select the best motif. So that's the selection process. And then we would later refine what we selected given the context of the song. So this process of creating, selecting, and refining, that's also out of context of today, the capabilities of today's deep learning AI. So now that we know what the problems are with AI music technology, let's talk about some strategies for the adoption of AI in the music industry. The first thing we can do is we can try to use the highest quality data for training our AI. So we can start with curated and verified music scores. The curation process, you can use some kind of music value metric, such as the Billboard charts. And the verified music scores, you can try to use music scores from the song publishers instead of MIDI files by unknown authors. And you can try to use the music XML format, which is actually very easy for a machine to parse. You would then engineer this data set into a lead sheet format and normalize it and segment it as appropriate. So using this high quality data to train our AI, we'll have a better chance of creating high value music. Another thing we can try to do is we can try to build an AI tool for each task. So this sequential process that I mentioned earlier, we can break it down into individual tasks and we can build an AI tool for each task. And what this does is it limits the context of this input to output mapping, so this X to Y mapping. So it's a little easier for the AI tool to understand what are the relevant features of X that can be mapped to Y. Another advantage of using this method is that after each task, you can allow for user selection and refinement. So the AI tool, let's say, in this task, will generate 20 motifs, and the user can then come in. So this is a user in a loop methodology. The user can come in and just select the best motif that the AI has generated and refine it themselves, and then move on to the next task. Another thing that we can try to do is we can focus on building AI tools that address tasks at the beginning of the music creation sequence. So the contribution to song value for tasks at the beginning of the sequence is higher than tasks towards the end. So for example, if we're trying to form the motifs into song sections, but the motifs aren't well written, then no matter what we try to do here, the song isn't going to improve much. So there is one advantage we can use. So tasks closer to the beginning of the sequence have less context. So there's less training, there's less data that's involved in the training of the AI. So it's actually easier to build tools that address tasks at the beginning of the sequence. Whereas tasks at the end of the sequence is much more difficult for AI because there's more context, so there's more data that has to be used for training. Fortunately, in terms of a human songwriter, it's actually easier for a human songwriter to address tasks towards the end of the sequence because there's more context. Whereas tasks at the beginning of the sequence is a little bit more difficult because in my opinion, it's more difficult for humans to create something from scratch. So here are the main takeaways, which summarizes my presentation. The songwriting AI is built with the following deep learning technologies. We have the autoregressive or time series AI models, and we have the encoder architecture, which maps data from X to Z to Y. Current AI technology cannot write a hit song on its own. When developing AI music creation tools, we should be focused on helping artists create hit songs. So this includes training the AI with high quality data, building an AI tool for each music creation task, and focusing on tasks at the beginning of the sequence. Thank you for attending. You can connect with me on LinkedIn. Just search for my name, Wayne Cheng, machine learning engineer, Audoir, and send me a message. I'll be happy to respond.